This is the next instalment in this series of little talks about the 200th anniversary of the Cambridge Philosophical Society. As I already said in an earlier talk, in 2019, we celebrated this anniversary with an exhibition in the University Library. The exhibition was divided into themes, and the theme I'm going to talk about this time is the one you can see on the left here. Unifying the sciences through mathematics. Now that may sound a little scary. I'm not going to show you any mathematics, but I'm going to try to give you an impression of why it's important in science and how it's been important through the history of the society. Here's a quote to start us off from a famous Cambridge scientist from the mid-20th century, G.I. Taylor, fluid dynamicist, and many other things. I think that if I were to start again, I should still try to be an applied mathematician because the number of amusing activities to which mathematics can lead one is so great. Now, that may not be your view of mathematics, but that gives a sense of, as it were, the professional scientist's take on the subject. We start our story before the society was founded. What I'm going to do is take a theme which is specifically to do with waves, various phenomena to do with waves, wave propagation, and the interference of waves. And that will carry us through a number of apparently unrelated branches of science. And that is the point about mathematics unifying things. The various subjects we're going to talk about, light, sound, X-rays, radio waves, these appear to be different. They all obey the same equations. And what that does for you is that it gives you a license for burglary. If you're studying a subject and someone else has already studied in a different context, something with the same equations, then you don't need to reinvent the wheel. You can take over everything they've done. So the story of waves and wave theory in Cambridge starts with this chap, Thomas Young. And in 1801 or thereabouts, he devised a famous experiment. The legend is that he got the idea through looking at the ripples on this pond in Emmanuel College. And he devised an experiment called Young's two-slit experiment. I'm going to describe it for you briefly here. And this is to do with light. So you shine a light in a single color, one color from the rainbow, at a wall with two slits in it. So these are the wave crests of the light waves coming in, and they pass through these two small slits, and you see what's being indicated here. The waves spread outwards in a sort of cylindrical way from each of the two slits, independently of each other. Now we put a screen somewhere back here where this dashed line is. What do we see on the screen? Well, a point like this, right on the midline, you can see that the wave crests from both the slits are arriving at the same time. So both the waves hit a peak at the same moment, they're in the same phase, and that means they add up to a bright light. We move up the screen to here, and again, we've got two lots of wave crests crossing. If you count, you'll find that it's taken one more cycle of the light to get from one slit than the other, but still the two waves have arrived in phase, and that's a bright spot. Halfway in between, like this point here, we're on a wave crest from one slit, but we're exactly halfway between two crests from the other slit. In other words, the wave there is at the bottom of a trough. So we have the peak of one wave, the trough of the other, and those cancel out. In the context of light, that cancellation means that it isn't light, you get a dark band. We'll be looking at sound in a moment, and the same equivalent cancellation with sound would give you silence from two sound sources. So you gaze at this picture for a little while, and you see that the prediction is that you should get a pattern of stripes, alternately bright and dark. Thomas Young did the experiment, and that is indeed what he saw, and that demonstrated conclusively that light really is a wave phenomenon. Now we move into the era of the Philosophical Society, and the story I'm going to talk through is very much tied up with the Cavendish Laboratory of Physics and the Cavendish professors. Now, the society, remember, was founded in 1819, and it had various purposes. One purpose was to give a forum for people wanting to do research to talk to each other. But it also acted as a pressure group on the university to persuade them to take science more seriously. Well, by the second half of the 19th century, that pressure group was succeeding. Furthermore, some money came in, and the Cavendish Laboratory and the Cavendish Professorship was founded, and that made experimental physics an official subject within the university. The first Cavendish professor was James Clerk Maxwell. I've listed the first few Cavendish professors here. The two that are in red are going to play a big part in this story, but actually most of them had something to do with wave theory and my theme. Maxwell is a case in point. We've already seen what Thomas Young did with light. Young's two-slit experiment demonstrated that light consisted of waves. Well, Maxwell was the one who put that idea on a firm mathematical foundation. He formulated the modern theory of electromagnetism, and one of the things that follows from that theory is that light waves, and as we'll see, other kinds of electromagnetic wave, obey exactly the same mathematical equation as sound waves. Sound waves are what we're going to turn to next, because we're going to come to Lord Rayleigh. Now, Maxwell, unfortunately, died very young, and really before the Cavendish lab had got properly going. So the university cast around for the person to take over this professorship and get the lab going. And they twisted the arm of Lord Rayleigh. Now, Lord Rayleigh is an interesting figure. In his student days, he had been a star of the mathematics course at Cambridge. But before the time we're interested in here, 1879, his father had died. He'd become the next Lord Rayleigh, and so he had a family business to run, and so he had not stayed in Cambridge. He'd gone back to the family home, which we'll see in a second. But the university prevailed upon him to take on this job for a 5-year span in order to get the lab going, which indeed he did to a splendid effect. And of course, the reputation of the Cavendish Laboratory is a worldwide brand name these days. So here we are in Lord Rayleigh's front garden and his country house at Tarling, a village in Essex. And here is Lord Rayleigh. Now, this is a picture of him later in life. The work I'm going to be talking about, he did much younger than this, even mostly before he took up the Cavendish chair. Why are we looking at a flight of steps? Well, if you stand where I stood to take this photograph, and then you clap your hands, you hear a very peculiar echo from this flight of steps. You hear an echo with a sort of musical note in it. And at least according to family folklore, the young Lord Rayleigh heard this and he thought about it a bit and he thought he understood what was going on. I should say that this is still the home of the Rayleigh clan. The current Lord Rayleigh, I think, is the great-grandson of our one that we see here. So what did Rayleigh think? Here's a little video of showing how here's his flight of steps. And the blue waves, these are sound waves coming in. Now, this is not at the moment the sound of a hand clap. This is more like the effect you'd get if you whistled. This is a single frequency sinusoidal wave being sent in. And you see what happens. You follow one of these blue waves and it hits the step and it gets reflected and turns into these red sound waves which come back. And the case I'm showing here, the wavelength is longer than the distance between the steps. And what that means, if you watch the set of red curves here, is that they're all in different phases. They don't line up. And this black curve at the bottom shows the total of all the red curves. And it is still a sound wave, but it's rather small. Now we whistle at a higher frequency. Now we've got a wavelength of sound which is too short for the spacing of the steps. Same thing happens, the blue waves reflect and become red waves. You add them up and you get the black thing at the bottom, but it's still rather small. But in between, there's a Goldilocks case. Here's what happens when you send in a sound wave with a wavelength that exactly matches the spacing between the steps. Now look at all the red waves. They're all lined up perfectly with each other. So when we add them all up, we get this big sine wave here. In other words, at this particular frequency, you get a really strong echo from the steps. Now, what I said you should do is clap your hands. Well, a hand clap generates lots of frequencies all at once, and they all reflect off the steps, doing the different things that we've just seen. And what this indicates, at least, is that out of all those frequencies you send in, this one, this Goldilocks case here, will be reflected louder than all the others. So the echo you hear has this musical note in it because this frequency, governed by the speed of sound and the spacing of the flight of steps, is stronger than all the others, louder, and you hear that as a tone. This is a typical wave interference effect. So Rayleigh wanted to do an experiment to verify this. A flight of steps is not a really convenient way to do an experiment. So he built some apparatus. How did he do that? Well, remember, he's not in Cambridge any longer. He's not retired, he's moved back to the family home to run the family's dairy business, but he didn't want to give up science. And indeed, he carried on researching for the rest of his life and became in due time Cambridge's first Nobel Prize winner for completely different work than the acoustics that I'm going to be talking about. Here's a couple of snapshots around Rayleigh's workshop and laboratory. It's still there. It's a wonderful time capsule. So isn't this just exactly how you think a lab ought to look like? Modern labs usually don't quite look like this. And his man, who no doubt sat at this bench here and used these tools, built this piece of apparatus. This is the original. We were able to borrow it from the Rayleigh family for our exhibition. And you see what you've got here. You've got 5 discs of muslin cloth attached to this curious scissor arrangement here. And I think you can see what happens. If you pull on this rod, slide it out, the scissors all expand a bit, all the discs move a little bit, but they preserve a regular spacing, but the spacing can be varied. So we've got regular cloth discs, regularly spaced, but we can change the spacing. So Rayleigh's experiment is going to be the equivalent of clapping his hand in front of the flight of steps. He's going to send a sound wave in and see what comes back. But remember, the magic wavelength is going to be something that matches the spacing of these discs. Well, they're very small compared with the flight of steps. They're only a couple of centimeters apart. And you do the arithmetic with the speed of sound, and you find that the sound wave you need is beyond the range of human hearing. It's ultrasonic. How do you do an ultrasonic experiment in the 1870s? Interesting. This is before electrical equipment had been invented. No microphones, no loudspeakers. Here's some more of Rayleigh's apparatus. He made sounds with these peculiar things here, which he called bird calls. You blew air through this side tube here, and by a mechanism that's a bit like the whistle on an old-fashioned kettle, it emitted sound, but sound you couldn't hear, ultrasound. Now, he's got a whole set of these. They live in a box, and underneath them, this is the lid of the box. And rather wonderfully, here is Rayleigh's handwriting on the piece of paper inside the lid of the box, and you probably can't read the small print here, but he lists the wavelength generated by each of these bird calls in millimeters. He was using millimeters in the 1870s. So he's got his reflecting apparatus with the muslin discs. He can make ultrasound with a known wavelength. how do you detect the answer? Again, no microphones, no oscilloscopes. The only way that sound could be detected back in those days was with this sort of thing. This is something called a sensitive flame. So you connect this to gas, normal household gas, and you light it inside here. And it's got a cunningly designed burner so that the flame is not very stable. And someone had discovered before Rayleigh's day that if there were big pressure fluctuations in the air around about this gas nozzle, then the flame looked different. It burned in an irregular way. So you couldn't measure the waveform of the sound, but at least you could tell if there was loud sound or quiet sound. And I'm calling it sound, but this works perfectly well with these ultrasonic frequencies. So armed with this equipment, bird calls, muslin discs, and sensitive flame, Rayleigh was able to do an experiment to verify the mathematical theory that he'd written down after observing his flight of steps. And this was one of the very early scientific demonstrations of what we would now call wave diffraction. Now, Rayleigh did something else. He was well aware, partly because of Maxwell's work, that light should behave in the same way as sound. And so he made a hypothesis, which is that iridescent insects, and here are some, and these are Rayleigh's own collection. These iridescent insects still live in these photographic plate boxes in the drawer of his desk in his study at Tarling. And again, we were able to borrow some of these for the exhibition. Rayleigh hypothesized that if only they'd had microscopes powerful enough, they didn't in those days, the electron microscope hadn't been invented, but that these iridescent insects would turn out to have either layers like the muslin discs or steps on the surface like the flight of steps. And that would be the reason that they produce this iridescent color. And we get a clue that Rayleigh was right simply from looking at these. Now, this butterfly wing must be well over a century old now. It's still brightly colored as it was when the butterfly died. If this had been a color caused by a chemical dye, it would probably have degraded and faded to a muddy brown by now. The fact that it's still bright suggests that it is indeed caused by what we would now call structural color. It's a wave interference effect. And this, in due time, was verified. Now, let's turn to a different kind of waves. Around about the same time as Rayleigh, in the late 19th century, X-rays were discovered. They were initially discovered as a nuisance. Somebody was doing an experiment in the same room that he had some photographic plates, and he found that his photographic plates got mysteriously fogged, even though they were wrapped up and protected from the light. Well, in 1912, a German called Max von Laue made a very interesting discovery. He found that if you shone these X-rays through a crystal and put a photographic plate behind it, you didn't just fog the whole plate, but here is von Laue's original picture. You got a pattern of spots. This was explained almost straight away in the same year by someone called William Lawrence Bragg. And if you remember my list of Cavendish professors, Bragg later became the Cavendish professor, a successor to Rayleigh. Here's a picture of Bragg, but again, this is later in life. He had this bright idea while he was still what we would call a research student. Now, his father was also a famous scientist, also called William Bragg. It's very confusing. And in the end, the father and son team wrote the definitive paper. Here is Bragg's original diagram with a geometrical construction based on the spacing of the atoms in the crystal. And on the left-hand side, his prediction of where the spot should be, matching exactly to von Laue's picture. And indeed, he shared the Nobel Prize with his father for this work. So this is the phenomenon of X-ray diffraction. And that became really, really important for Cambridge science later in the 20th century, because it led to all the stupendous work on molecular biology, a whole string of Nobel Prize winners, Watson and Crick for DNA, Perutz, Kendrew, there are lots and lots of them, and it still continues, all based on Bragg's insight on how you could interpret an X-ray diffraction pattern, provided you could persuade your molecule to crystallize, and that was the clue to doing DNA and so on, then you could get a diffraction spot pattern. And if you worked hard enough, or these days got your computer to work hard enough, you could work out the form of the molecule. So here is Sir John Kendrew. He's an example. He studied the molecule myoglobin. This is Kendrew's original diffraction spot pattern for myoglobin. And here he is standing next to a large-sized model of his molecule. And like these other people we've been talking about, he got the Nobel Prize for this work. All based on wave theory, different kind of waves. We've had light, we've had sound, we've had X-rays, all based on the same mathematics. Lord Rayleigh would have understood everything. If you go to long wavelengths, X-rays have really, really short wavelengths, shorter than the wavelength of light. Long wavelengths take you into the world of radio waves. Well, here is the radio telescope just outside Cambridge, and the position of this array of dishes is by no means random. Someone has taken advantage of wave interference theory to place this set of dishes in such a way that they focus the combined beam that ends up in your computer from listening, as it were, to what comes into all these from radio waves coming from distant objects in the universe, quasars or whatever they may be. Again, the same wave theory. And finally, a picture that brings us right up to date. Wave theory is still important. Here is an image, a microscopic image, and you see all these colored spots here. These are nanoparticles. These are very small indeed. And those colors you're seeing are not the result of the particles being colored in the sense of having a dye of some kind in them. They are colored as a result of wave effects. The individual particles are so small that they have patterns of electromagnetism around them, roughly the same as what Lord Rayleigh would have called normal modes. And so by tailoring the shape and size of your nanoparticles, you can make things that have particular colors. So here is a theme that goes from just before the Philosophical Society was founded and takes us through the whole 200 years right up to the present, all taking advantage of this synergy between different kinds of waves because they share the same kind of mathematics.